Okay, well, we're going to take a look at a couple additional examples of using derivatives to solve some problems. One associated with flow volumes in a stream and another with seismic intensity. So in the first problem, we're interested in determining what the volume of water is that flows past a point in the stream. We're given that the velocity is 5 feet per second. The stream has a semicircular cross-section, so its area is 1/2 pi r squared. And we're also given that it has a diameter equal to 10 meters. So the volume then is just going to be the cross-sectional area times some distance, which we have to determine. We could just say, well, it's 10 feet. How much volume is in 10 feet? But we're kind of interested in how the volume of water flowing past a point varies with time. So we have our basic relationship for the volume. And in order to figure out how that volume varies as a function of time, we're taking the derivative dv dt. And that is just going to be the cross-sectional area, or 1/2 pi r squared, times dx dt. So we have our cross-sectional area here, dx dt over here. Our dv dt is equal to 1/2 pi r squared v. dx dt is just a velocity. And the volume flowing past a point along the stream bank in a certain time, dt, is going to be 1/2 pi r squared v times dt. Notice that the units of the velocity times the time are just going to give us a distance. So we get this distance, but in this case the distance is related to a certain time of flow. Okay, over here you'll notice that we have a problem. It's a problem. It's definitely a problem for me. We've got units over here. The velocity is in feet per second. The diameter of the stream cross-section is 10 meters. So we've got to either convert velocity to meters per second or the radius to 5 meters. Or to feet. So what I've done here is I've just converted that 5 meter radius to 16.4 feet. So we have 1/2 pi r squared. That gives us 422.5 square feet in the cross-section here. The change in the volume, dV, in a certain time dt is just going to be the cross-sectional area times the velocity times the time. And so we have our cross-sectional area. We've got the velocity here. Oops, left out a parentheses. 422.5 square feet times 5 feet per second in a certain interval of time. If that interval of time is 1 second, that gives us 2,112.4 cubic feet. If we're looking at the volume of water that flows by in 1 minute, it's 126,744.4 cubic feet. So a simple use of the derivative. Basically, the derivative is giving us the velocity component from our cross-sectional area, and then we're using that to evaluate the volume of water that's flowing past a point in a certain interval or certain intervals of time. So a pretty straightforward example. The second example involves the intensity of illumination from a seismic source located at a source point location, located at an elevation or a height above, some height above the surface here. And we're interested to determine this distance that will maximize the illumination of the circumference at this radius r. So you can see psi is this angle, d is the ray path length. If we take a look at this diagram, remember d psi is a really small angle, so it's collapsing onto a ray path which extends down from the source. But notice if we kind of expand it out, that the diameter of a cone that extends around the disk, right at this point, the conical region of the mechanical disturbance has a distance L0 for this d psi. Over here it has a distance L psi. And this distance increases as the sine of psi. So this distance over here is going to increase from its distance over here immediately, directly beneath the source. We're interested to determine the source elevation so that we maximize the illumination along the circumference. So in equation form, then, we have intensity. We're saying that it's proportional to the sine of this angle divided by d squared. That's this distance here, or over here. And d is just going to be equal to x squared plus r squared to the 1/2 power. And the sine of psi then is just going to be the side opposite over the hypotenuse, or x over, this is just basically going to be the height of the source above the circular surface, x over x squared plus r squared to the 1/2, which is the distance d from the source to that point. So k is just a constant of proportionality. Substituting that in, we get that the intensity is equal to k times x over x squared plus r squared to the 3/2 power. So this is the function which describes the intensity. And we want to determine the minima and the maxima of functions, or we have to recall at least how we want to find the maxima in this case. But recall how we do that. First of all, we have to evaluate the derivative, and then we have to set that equal to 0 and solve for x. So using the quotient rule, I'll leave this as an exercise for you. You might take a few minutes and see if I've made a mistake here. But di dx, we're differentiating this function with respect to the independent variable x, and we get that this derivative as a function of source height is k times r squared minus 2x squared over x squared plus r squared to the 5/2, and we have to set this equal to 0 in order to solve for an x that will maximize the illumination at a point along the circumference, a distance r from the center of that circle. So di dx is equal to k times all this is equal to 0. That's going to be equal to 0 when r squared minus 2x squared, the radius, squared minus 2 times the square of the height of the source is equal to 0. Or when x is equal to r over the square root of 2. So we've expressed x in terms of the radius here. And so now we have to evaluate the second derivative. We know what x is. When this derivative is equal to 0, we know that x will be equal to r over the square root of 2. But we have to determine whether, for a maximum, the second derivative is going to be negative, right? When x is equal to r over the square root of 2. So we have to confirm that. So the second derivative here, we're just kind of going through the showing parts of the second derivative. We find that the second derivative then looks like this. And again, this would be, we have one term with x squared plus r squared to the 5/2 power. And we have another term with x squared plus r squared to the 7/2 power. And so it looks like a pretty messy relationship, but we want to evaluate this expression at x equal r over the square root of 2. And when we do that, and I kind of leave that to you as an extra, both of these as an exercise, taking this derivative, and then also evaluating the second derivative. Well, see this minus sign in front? It's approximately equal to k over r to the 4th power, and negative k over r to the 4th power. So, the second derivative is negative, which means that we have a maximum. So, we know that I will be a maximum along the circumference for x equal to r over the square root of 2. And we'll leave it till next time to discuss this problem from a more conceptual point of view using graphical representations of the function. And then we'll also introduce another problem where we're standing on a mountain, the mountain's so high, and what is our line of sight? In other words, what is the distance to the horizon from our point of observation? So we'll see you next time.